Hello, my name is Cristian Leonardo Pabón Rojas, and I would like to comment on the work entitled Airfoil Optimization for Small Horizontal Axis Wind Turbine. The work was carried out within the framework of a project aimed at the design, simulation, and construction of a wind turbine for low wind speeds using biocomposite materials for natural fibers found in the country. The project compares two turbine designs, one in a vertical axis and the other with a horizontal axis, to select one of which a prototype will be built for further study. This project is part of Seneca, which is the Alliance for Energy Sustainability in Colombia that seeks to diversify the country's energy sources, strengthen the transportation and industrial sector, and mitigate the effects of global warming. The objective of this work is to try to impact the areas that do not belong to the interconnected zone, which in Colombia are about 50% of the territory. These areas are difficult to access. For that reason, the communities do not have access to many sources of electricity. In particular, we want to use wind energy since by 2017, only 0.4% of the wind potential of the country have been used, and that is distributed through the country in very usable winds in the north of the country, but in the continental zone, it doesn't exist 7 meters per second. The design of a small-scale turbine, a microturbine, is intended to be simple to build, easy to transport and install, as well as easy to maintain if necessary. Also for these areas of difficult access to be used to cover part of the energy needed for devices or tools in use in remote areas. Okay. Taking into account these aspects, the operating conditions for which the turbine is being designed is that it can work with a wind speed of 4 meters per second. For the case of the horizontal axis turbine, a rotor diameter equal to 2 meters and with 3 single blades with a power coefficient that is in the range of 0.25 and 0.45, and which is expected to work at Reynolds numbers below 300,000 due to the low wind speed and also reduced core size. It is taken into account that for turbines and blades, a Reynolds number is considered low, below 500,000, where different phenomena and problems can be found that can affect the efficiency of the horizontal axis wind turbine, because here its operation is based on the lift by the fluid passing around the blades. One of these problems is the separation of the boundary layer of fluid that can be transferred into a separation bubble by itself. Only with the separation of the layer, this generates left lift, also good if it were a bubble. The impact of the fluid in a turbulent weight generates an increase of the drag, and this drag affects the efficiency of the turbine. Due to these disadvantages that occur at low Reynolds, as a first step, a selection of airfoils to be used in blade areas is carried out. From this first analysis, the airfoils of the SG64X family were selected. More specifically, the SG6043 and SG6040 airfoils. The SG6043 was selected for the middle zone and the zone near the blade tip, which showed more aerodynamic conditions, and the other one for the root zone with a greater thickness to support the structural load. It should be noted that in this comparison and this selection, airfoils that were designed for Reynolds numbers below 500 thousand were chosen, as is the case of this family of airfoils that was designed for Reynolds numbers between 100,000 and 500,000. Below, we can see the comparison curves. On the left side, there is a comparative graph for the airfoils intended for the mid-blade area, where for a Reynolds numbers of 100,000 was compared the relationship between the lift and drag coefficient versus the angle of attack. There is found that the airfoil with the highest curve was the BW3, followed by the SG6043, which was selected at the end because its curve didn't have so abrupt changes between each degree of the angle of attack, and may be advantages for possible changes in wind speed suffered by the turbine. On the right side, where we can see the comparison curves for a Reynolds of 50,000 of the airfoils that were being evaluated for the root zone, it can be seen that there is not much difference between the different airfoils, which leads us to select the SG6040 airfoil for its relation with the SG6043 airfoil, since being of the same family, their geometries are not very different. As a tool for the evaluation of the different airfoils, the Xfoil software was used, where the Reynolds numbers was taken into account as a parameter for the analysis. Okay, let's go to the next. Once the airfoils were selected, the process of optimizing the selected airfoils began. The objective of the selection was to have a more promising starting point than to start generation an airfoil completely from scratch. As a parameterization method, the Bézier curves method was used, in which 13 control points were used to control the shape of the airfoil geometry and which allowed moving a single point to obtain a different geometry by means of an algorithm based on gradients that use Xfoil itself within its code to evaluate the performance of the geometry. Everything was an interactive process with which the modified airfoils that will be part of the wind turbine blades were obtained. Each selected airfoil underwent the same optimization process, from which we can highlight these graphs, where on the left side, we compare the performance based on the lift coefficient over the drag coefficient versus the angle of attack for a Reynolds of 50,000 calculated due to the chord size obtained in a preliminary calculation, and where the airfoils SG6040 and its optimized version called RISE are compared. In this graph, we can notice how the optimized airfoil curve is higher than the base airfoil and with less steep slopes. For the middle zone, SG6043 was selected and also optimized, where on the right side we can see a comparative graph for a Reynolds numbers of 100,000, and where the base profiles SG6043 and its optimized version MET do not have much difference in the values of the lift drag ratio, but we can appreciate a curve with less steep slope in the MET profile. Moving on, I must say that from these obtained airfoils called RISE and MET, the calculation of the values for the chord and pitch angle along the blade is performed. The graphs that we can detail on the right side of the slide show that the chord sizes near the root reach values close to 15 centimeters and at the tip reach just over 2 centimeters. The method used to calculate the geometry of the blades is the BEM method, or blade element momentum theory. After obtaining the geometry of the turbine, numerical simulation analysis are carried out using CFD software, which are still in process. For this analysis, the turbulence model K omega SST is being used, from which rotation speed close to 230 revolutions per minute have been obtained, which are low for the expected ones, since the calculation was made thinking of a speed close to 260 revolutions per minute. For this reason, the work is still under study fluid dynamic. In conclusion, it should be noted that with the optimization method used, the airfoil called Suarez, compared to its base airfoil SG6040, obtains a higher aerodynamic performance of the efficient lift ratio coefficient over the drag coefficient for different angles of attack, and that the airfoil in the med zone, although it does not exceed the values reached by SG6043, has a behavior that can be considered favorable. Okay, at last but not least, I would like to note that the authors gratefully acknowledge the financial support provided by the Colombia Scientific Program within the framework of the called Ecosistema Científico. Okay, and that's it. Thank you very much for your attention. Have a great day and night.